So tonight we're going to talk about finding the derivatives of inverse trig functions. Later, when we start taking derivatives at specific values, we'll need to keep in mind the domains and ranges of these functions. So take a minute right now and see if you can think of what these functions look like graphically and what their domains and ranges would be. Press pause, then check back. So these functions, inverse trig functions, just like any inverse, these functions are flipped over the line y equals x. So inverse tangent looks like this with its asymptotes horizontally instead of vertically. And its domain and range, sorry about that, are here. Sine and cosine, arcsine, arccosine similarly are flipped around, and they end up looking for arcsine like this. Here we have what was a maximum, and here we have what was a minimum. So our domain is now from -1 to 1, and from -π/2 to π/2 is our new range. Sorry. There we go. Cosine is similar. We can only take a piece of each sine and cosine because they're periodic, and if we took the whole thing, they would no longer be functions. So we only take a chunk from the maximum to the minimum. Again, here's a minimum, here's a former maximum. Imagine I can draw. And this has a x value of 1, an x value of -1, and goes from 0 to pi. Again, just things to keep in mind for when we start taking derivatives of inverse trig functions at specific points. For now, we can ignore domain and range for just a little bit. So we're actually going to derive the derivative of each one of these. It involves some complicated steps. Follow closely, and you're going to try some of these on your own as well. I don't know how to take the derivative of arcsine right away, so I'm going to put it into a form that's much more familiar. I'm going to write it in terms of sine. Now I can take the derivative. Go ahead and differentiate implicitly. Press pause. Again, I don't really need to pay attention to the domain and range right now, so I'm just going to put them away. But when I differentiate implicitly, don't forget you end up with y prime inside of your derivative. Okay? That has to be there. Go ahead and solve for y prime. Press pause. I've solved for y prime, but now I have a small problem. I have cosine inside my function. Remember, my original function was arcsine of x. So I need to have x somewhere in my derivative, and it's not there. So I do have a relationship between sine of y and x, but not cosine y and x. If I can make a relationship between cosine and sine, then I can make a relationship between cosine and x. So think of your trig derivative, your trig IDs. Cosine squared plus sine squared is 1. So if I solve that for cosine squared, I get 1 minus sine squared. Well, I don't have cosine squared, but I do have cosine, so I can take the square root of both sides. Now I have a way to substitute in for cosine of y, but it still has that y in it, sine of y. But that's okay, because I know that sine of y equals x, so sine squared of y must equal x squared, and that's how I made this substitution. Phew, a lot of substitutions, but we're still not done. My goal, remember, was to find an expression for y prime, the derivative of arcsine. So, if I move these around, we can see a little better. I'm almost there. I have my substitution for cosine of y that I can put right into my derivative from above. So now I have an expression for the derivative of arccosine in terms of x. We're going to do something similar for arccosine now. Very similar. Again, go ahead and rewrite as a cosine, not an arc cosine, and take the derivative implicitly. Press pause, then check. So I rewrote in terms of cosine, took the derivative implicitly. I have a y prime in here, so our steps were rewrite, take the derivative, and we did that implicitly. And now we're going to have to make some substitutions after we solve for y prime, because I have this sine y in the expression. I know what cosine y equals in terms of x, but I need an expression for sine y. This is very similar to what we did before. Think of the relationship between sine and cosine, make a substitution, and then you're going to make a second substitution once you actually have cosine in your expression. Press pause, give it a try. So, I know that sine y is equal to the square root of 1 minus cosine squared y. Very similar to what we did before using the Pythagorean trig ID. And here I made a substitution because I know that cosine y equals x from my previous step up here. So now I can make this substitution into my derivative and get a derivative in terms of x. Voila! This is the derivative of arc cosine of x. Take a wild guess as to what we're going to do next. We've done sine, we've done arc sine and arc cosine. That's right, arc tangent. So here, I've actually laid it all out for you, but I just hided it. So go ahead and try the process we've been doing. Rewrite, take a derivative implicitly, make some substitutions until your derivative, y prime, is in terms of x, not y. Press pause, try those steps yourself. So I've rewritten, I've taken the derivative implicitly, I've solved for y prime, but I've got this ugly secant squared stuck in my derivative. Tangent and secant have a special relationship. Secant squared y, in this case, equals tangent squared y plus 1. So I can substitute directly for this secant squared, and I know that tangent is equal to x. So I'm going to be able to substitute for tangent squared as an x squared. My last step, like I said, substituting for tangent squared and x squared. And so here's my derivative of arc tangent of x. Phew. Guess what? There are 3 more inverse trig derivatives we need to figure out. Hang on a second, though. There's something else I want you to think about. What happens if we don't have something like x as our input? For example, what if we don't have y equals arc sine x, but we have something a little more like y equals arc sine of 2x? You know something about chain rule. You know something about taking derivatives of inverse trig functions now. Take a guess. Write down your guess, and we're going to prove the derivative of arc sine of 2x in the next few steps, using a very similar method as what we did before. We're going to rewrite, take the derivative implicitly, solve for y prime, and make some substitutions. Press pause and try those steps yourself. So, again, following similar steps, I rewrote, but this time I actually decided to solve for x. Not a necessary step, just helped me along the way. Then I took the derivative, and now I need to figure out how I can substitute for cosine of y. I could also at this stage solve for y prime, which equals 2 over cosine y. But I still need to make a substitution for that cosine, and I remember that I've got a relationship between cosine and sine, but I also remember that I have a relationship between sine and 2x. So that's where this came from, those 2 substitutions over here. And so I can substitute for my cosine of y using what we learned up here, and I have a new expression. So this is the derivative of arc sine of 2x. Was it what you guessed it would be? Interesting. So I've got another question. I have this thing, 1 divided by square root of 4 minus 16x squared. It looks a lot like one of our trig derivatives, our inverse trig derivatives. It looks a little like the inverse trig, the derivative of arc sine. But there's this funky 16 and 4 happening, and I still have this 1 on top, which is a little different from the problem we just did, where we had a 2 on top, and we had 1 minus 4x squared underneath the square root sign. That was the derivative of arc sine of 2x. This looks similar, but there's something weird. That 4, that 16. How could we turn this expression to look like it might be a derivative of an inverse trig function? This is really just a thinker. I'm not going to display how to do this. We'll come back to this again and again, especially when we get to anti-differentiation, which is the reverse of taking a derivative, underivativing. So just leave it as a thinker, ponder for a while, press pause. Like I said, the very last thing I wanted to talk about was these last 3 inverse trig functions. But I want you to be ready to discuss in class how we could find their derivatives using the same basic steps we did before. Rewriting in terms of secant or cosecant or cotangent, taking the derivative implicitly, solving for y prime, making some substitutions, and eventually getting our y prime just in terms of x. So be ready in class to think about these. I'm not going to show the steps here, but I want you to be thinking and ready to try them. Might be a good idea to get some ideas on paper before you come to class. That's it. Thanks and have a good night. Don't forget to do any book problems that are assigned.